Okay, everyone. So this last part of the chapter talks about the idea of laws and theories and principles and things like that. And I want to discuss this just a little bit. And specifically, I want to clear up some things just because of the way that words are used. So I want to make sure that you understand um, that in particular so that you can use it when people try to tell you things that are false. So first of all, what we call laws in nature are in general um, accepted scientific principles that have been shown and tested over and over, time and time again, to be true. Um, Things like um, Boyle's law, which I believe relates the pressure and volume of a gas, um, or the ideal gas law, or even things like Newton's law of gravitation. These things over and over, you can test them, and they're determined to be true. Now, in addition to laws, you have things that are principles. Principles are also descriptive in the way that you can test them and show that they're true, but they're generally more specific than laws. Things like Archimedes' principle relating to the buoyant force that an object feels when you submerge it in water. It's more specific about something specifically being submerged in water. Everything is going to experience a force like gravity. Everything is going to experience electromagnetic force if it has some kind of electric charge to it. But principles are more specific to specific situations. Now, the issue with the way that words are used comes about mostly when we talk about the word theory. In science, a theory is basically a collection of hypotheses that are known and accepted and have been shown to have been tested over and over again. The word law really has been kind of retired to older things, and nothing is really considered a law now. There are certain laws in science, like the law of energy conservation, the law of mass conservation. These things, though they're laws, the law of universal gravitation, or the ideal gas law, once they're put to the test, now we can show that there are things that are different about them. For example, we refer to Newton's idea of gravity as the universal law of gravitation. However, it's been shown recently, or in the past 100 years, that that is not a very accurate representation of everything in the universe. More specifically, it's been replaced now with Einstein's theory of general relativity. And that theory of general relativity is known and tested and has to exist. It is required for the GPS satellites that you use in your phone. If we didn't account for Einstein's theory and instead just use Newton's laws, then our GPS systems would not work. So something we call a law has been replaced with something we call a theory, even though that theory is pretty well proven. What happens is, in society, people take the word theory to have a different meaning, as in, your friend does something strange and you have a theory about why they did that. Those are two different things. In science, theory refers to something that's well understood and still tested. It's a collection of ideas. It just means that in the future, something can come along and change those ideas. We're willing to accept the fact that facts can change based on new evidence. And that's essentially why everything's a theory now, and there are no more laws. That does not mean there is no support for them. It does not mean that it's just somebody's idea. It just means the scientific community understands things can change, and they have over the course of hundreds of years. Finally, models are more of a way of applying theories and applying our understanding to the way that we approach a system. For example, when we talk about models, a perfect one to talk about right now are weather models and models for hurricanes. We take all the known theories and ideas and how we understand weather and air motion and how hurricanes intensify, and we combine all of those things together to generate a model that will show us what we think will happen with those particular storms. Models just use theories in some ways to be predictive. They also use theories in some ways to show things that you can't always show face to face. Another good representation of a model is a model of the solar system. You can build a small, reasonably scaled model of the solar system that still shows the distance between planets and still shows the size difference between planets, but it's small enough for you to represent it where you could hold it or see it. And so it's representing a larger system on a smaller scale. We also use conceptual models in science to understand things like how chemical reactions occur. Shell model of an atom is essentially a conceptual model to understand how electrons collect on the outside of an atom. A true understanding of an electron requires way more specification and complexity. But we use a simplified model so we can talk about it. So models can take information that we understand and theories and apply them, or they can just take situations and simplify them for us to understand further. One other example is we can show the model of a rainbow. If you see a rainbow in the sky, always look, because there's likely a double rainbow, there's likely a second rainbow you can see. And one of the greatest things about that is the colors of that second rainbow, though they will be fainter, they will be inverted. They'll be in the opposite direction of the smaller rainbow. So look for that too when you see this. But you can model a double rainbow by just understanding how a ray of light will refract and bend inside of a drop of water. And understand that when sunlight hits water, light will reflect once and you get a nice bright rainbow, but it can also sometimes reflect twice. And that second reflection occurs naturally, not as often and not as with much intensity, and so you get a dimmer rainbow.